Good morning for everyone. Today is a wonderful session that is electric propulsion and the recute generator. A lecture by Mr. R. Harford, PhD at APS Department in Sikorsky Care Polytechnic, Ukraine. He is the founder of Novel Space Concepts LSCC. First of all, I would like to welcome our Mr. Aaron Harford, and we are thankful to them for accepting this event, and also welcome the all participants. I will give the session to Aaron sir. Sir, can you?
Ah, okay.
Sir,
Well, thank you all for having me. I'm excited about this. Uh,
sir,
so
take a session, sir.
uh, please forgive me. I may take a sip of coffee, and I do have a cough drop. I am recovering from, I had COVID about a week ago. So I'm still okay, but it's not bad, but it's something that we're all just dealing with. So, yes, my name is Aaron. I am from Los Angeles, California, but I live in Kyiv, Ukraine. Some people ask why Ukraine, so I might as well get it over with. Um, my grandparents are from Ukraine, and my wife is Ukrainian. So, 3 years ago, I came here. Just wanted to get outside the United States and travel and have a different perspective. And I thought, well, I might as well come here because I have family here, and it's, reconnecting with my family's roots. So KPI, I'm a PhD student in the electrical engineering department, and so why come here and do this? And people say, oh my goodness, you have great schools in the United States, and that's true. But I spent 8 years teaching in the United States in the university system, and most of my adult life was in the higher education system. And I found that if you want a more meaningful education, education should be when we challenge our thinking and are open to new ideas and different perspectives. That's what my understanding of quality education is. And if all we do is sit in the same educational system and get the same point of view, that's not very open. And so I always had a lot of respect for the engineers coming from this part of the world. Of course, Gagarin, Sputnik, Sikorsky, KPI is where Korolev, who was the chief designer for the Soviet space program, he was born in modern-day Ukraine and attended KPI. And Igor Sikorsky, of course, who invented and developed the helicopter, he fled to the United States after the Bolshevik Revolution, and another just amazing engineer. So the history of engineers in Ukraine, it's definitely in their blood, and it's something to be proud of. And so I wanted to come and get that perspective. And so that's what I've been doing. It's pretty amazing. I first came across electric propulsion when it was a year. Well, I had heard about electric propulsion for many years, ion propulsion mostly. But ion propulsion, it's very efficient, but it also doesn't have much of a thrust density, and it only works in space and maybe low Earth orbit for correcting for satellite orbits. But even with ion propulsion, the pressure is about that of a piece of paper on your hand. And I don't know exactly what extent all of you are familiar with this. So I might be a bit too simplistic on it, but this is just 30-minute lecture and my first class here. So I came across a researcher by the name of Bolonkin, who was engineer in the Soviet Union for Antonov, and I was researching just some different ideas for a dissertation topic, just kind of really being open. We were on quarantine. I was out in a village. I had an internet connection and a car, and that was about it. And we didn't go anywhere. So I was just free to kind of explore and see what I wanted to do. And I came across an article for space towers, inflatable space towers to like 100 kilometers. And I just thought, whoa. And I was really impressed because not only were these really imaginative ideas, but they were possible. They were grounded in practical materials, physics. It wasn't, antimatter, warp drive. It was like, well, we can't build a space elevator yet, but we could make a tower to about 100 kilometers with inflatable modules. And you start with steel and concrete, and then you use air, and then you use hydrogen, where it's up so high that there's not enough air to burn. And I just thought it was really fascinating. So I emailed the author, and it turned out he was alive and living in New York City, in Brooklyn, still publishing and writing at age 86. Uh, and he says, "Oh yeah, that's a great idea. It's very interesting about space towers. But if I were you, I would focus on electric propulsion. Here, look through some of my articles, just different research ideas, and we'll go to it." Um, and I found his article on a hypersonic electric ramjet and started to read some of the history of it. That if you use very high voltage, low current, you can produce a thrust, and not just a thrust from ionization, but also just from the electrons themselves. Once you get up to about 10 million volts, which, yes, is like crazy high voltage, but we need to be imaginative and open to what's possible. Once you get up to about 10 million volts, the electrons themselves start to have mass, and you can use those as reaction mass. Now, you don't want to get caught in that exhaust, the exhaust of an electron engine. But so I started to look at it, and so I'll go ahead and get into it. Um, I can share a bit about. Let me share my screen. Okay, go ahead and share my entire screen. And can you see the PowerPoint? You should be able to in just a moment. It's loading. My system is slow. Can you see the presentation? Anyone? Hello? Okay, well, I'm going to assume you can. Okay, so electric propulsion, and the ELECTRET generators required to make it a reality. So I'm a PhD candidate at KPI, Igor Sikorsky, because it really comes down to, yes, we have these propulsion ideas, and there is a lot. It's a new field of research, or it's more of like a resurgence, but it's a lot more popular now. So about me, of course, PhD candidate at KPI in Kyiv, Ukraine. I did work on rockets for a small company out of Mojave, California. And it completely changed my perspective, because out there in the desert, I saw that small teams, 5 people, 10 people, with relatively small amounts of funding. I mean, even in the United States, $1 or $2 million for aerospace is absolutely like laughable. Boeing, NASA, all the big contractors and agencies, they won't take it seriously. They just, but what I saw is these small teams were building real hardware. And when I got to wake up in the morning out in the desert, and there's nothing there. If you're looking for, Hollywood glamour and all of that kind of thing in nightlife, don't go to Mojave. But if you want to build spaceships and you like that pioneering environment, then absolutely go. So out there, we were working on rockets for small satellites. And most of the time, what they work on doesn't work. And that's where I lost my fear of failure out there. We're going to build something. We have an idea. We go build it in the shop. It probably won't work, or it won't work how we want it to. And then you go back and you try it again, or you do something different. And it really showed me that, if you want to do something groundbreaking, be prepared for failure. In fact, embrace it. People might laugh, not take you seriously. It doesn't matter. As long as you're based, like Elon Musk says, based off of fundamental principles. Look at the fundamental, simplest variables of the problem and go from there. And you won't always be right. And sometimes we oversimplify things. But look at the fundamental variables interacting in this problem and how can we deal with this. And so when I looked at the electric ramjet, it made sense to me. This is a quote from Interstellar, Christopher Nolan, but where they're deciding they're going to use the black hole slingshot around it, and he says, "Yeah, I forget which AI, but the AI says Newton's third law: the only way humans have ever figured out of getting somewhere is to leave something behind." And that's true. So we're going to talk about fundamentals for propulsion. Of course, Newton's third law: every action must have an equal and opposite reaction. We can't get around that. It's fact. And so for rockets, the uncomfortable truth is that we have the Tsiolkovsky rocket equation, and Tsiolkovsky is a very interesting figure to read about as well. I was a Russian. Ended up being self-educated. He had some sort of disease. He couldn't really hear. And so he was self-taught, and he came up with these amazing ideas. But he came up with the rocket equation, that a rocket can apply acceleration to itself by expelling part of its mass at high velocity. They call it the tyranny of the rocket equation. And it's true, because if you want to make it bigger, then you need more fuel. And then you need more fuel. Well, now it's got to be bigger. Well, when you make it bigger, now you have more problems. And then people try to go smaller. Well, okay, that works to an extent too, but you've still got a problem. 93 to 97 or 98% of rockets are fuel and oxidizer. And this is a real problem because it means no matter what we do, and I love rockets. They're exciting. It's interesting. They are the present and they're the past, but they are not the next step. So when I read about BOLONKI'N's idea, and it wasn't just him, there were others, but he was the first one that I read about in a coherent article that put it all together. Electric propulsion can help advance propulsion technologies because you're not using fuel and oxidizer directly for reaction mass. Now think about that. All of our propulsion, whether it's jets or rockets, we're burning something, whether it's fossil fuels or hydrogen, oxygen, doesn't matter what it is. You're burning something in a tube of some kind and expelling it out the back. There are problems with heat. In fact, rockets are not efficient. We hear about how we need efficient propulsion. That doesn't hold true for rockets and even internal combustion engines. Burning things is not an efficient use. You can even compare, like, for example, a tree. You've got 3 different uses. The tree can live for its lifetime, give off oxygen, be a home for birds, and so forth. That's one use. The other use is cut it down, build a house, and live 2-3 generations in it. It's dead, but it's more efficient. The last way is to burn it. We're just going to burn it. Well, that's what we're doing with rockets. It's necessary, but as far as looking to the future, it's not the answer. With an electric engine, you can accelerate any reaction mass virtually. And so that's one of the appeals. You're not heating the reaction mass, so we don't have the stresses on materials. Think of all the stresses we have on jet and rocket engines. That's the key failure point, because at some point, every known material fails. Even with hypersonic jets, once you get Mach 6, all known materials fail, and we can't fix it, and it's not very efficient. But a hypersonic electric ramjet It's very different. It has its own problems, but if you think about it from the fundamental concept, we're not burning something in an engine anymore, at least directly. So Bolonkin's engine, like I was talking about, so an air-breathing electric ramjet, and there is so much research on this. I have a couple of articles at the end, and maybe we can do some more things on this. But I've reading through dissertations, articles, but you're going to find very little historically on ELECTRET generators. But so the air-breathing ramjet, like I said, it's a solid-state engine. It has no moving parts. It does not heat the reaction mass. And actually, the efficiency increases as velocity increases. So because you're using electricity, electric forces, you don't have the problems that you're going to with combustion. You have other problems, but that's something else. The ability to utilize almost any reaction mass. You can use the atmosphere on Earth. You can use the atmosphere on Venus, Mars, Jupiter. You could even land on an asteroid, process the asteroid, and run it through the engine. That's pretty fascinating. Now we're talking futuristic propulsion, because imagine a workhorse engine that has no moving parts and can utilize almost any reaction mass. And that's really what turned me on to this and thought, whoa, even if it doesn't work or we encounter problems, this is a worthy goal. An electric engine that could make interplanetary not just travel, but commerce. And I mean, it means you can get around the solar system and possibly even interstellar, given enough reaction mass. So with all of this, of course, I saw there was a problem. And it's one of the reasons I suspect why they were not pursued more back in the 1960s. You need the ELECTRET generator. And ELECTRET generators, they're high voltage, low current. They have a long history. Few people want to deal with them for good reasons. There were a lot of deaths and injuries in the early days of electricity research, and that was done with electrostatic or ELECTRET generators. You had the influence machine, the Wimshurst machines, Van der Graaf machine. They've had their uses, and they still do. They were used in early X-rays, particle accelerators, and one of the issues is, yes, you're dealing with very high voltages, and you're essentially running your engine on lightning. And for the most part, magnetic generators make more sense for most applications. They're almost 100% efficient. They're relatively safe. We've had 200 years of development, historic investment, development. We know how they work. However, for aerospace applications, magnetic generators meet limitations. This is where ELECTRET generators make sense. Current magnetic generators, they're too heavy. And when AC is very common. If you want to go from AC then to DC, of course, you need a rectifier. And for aerospace, if you go from a traditional AC or even DC electric generator, you're going to have a rectifier. You're going to have to, in the case, if you use a DC magnetic generator, you still have to up the voltage. And that, again, requires more equipment and hardware. So by the time you do all that, it makes no sense for flight. And right now, there are no industrial electrostatic generators because we haven't really had an application that justified it. But this, I believe, does. This is exciting enough, and it makes enough sense to develop. And it's actually being developed. Different teams around the world are focusing on different aspects of it. Now, the other reality is, on Earth, we have a power problem. we're going to have to use a jet turbine to turn the non-existent electrostatic generator to operate the theoretical thruster. Yeah, that's one of the downsides. People say, well, why are you using a jet turbine? By the time you do that, just use jet turbines. And they would be right. And I think that's why we haven't pursued it. Because yes, jet turbines are, they're developed, they've worked. You don't have lightning in your engine that could go wrong when you put people on it. But if we talk about the future of propulsion, the next step of propulsion, it's not going to be just burning things. And when microturbines are used for power generation, the wear on the engine is much less. I mean, look at a hybrid car like a Tesla, or not Tesla, but like a Prius. That engine has a very easy life. It's a very limited RPM. It's optimized for a certain rotations per minute life cycle. Internal combustion engines on a Prius last a very long time. And even jet turbines used for power generation have different wear characteristics. And that's a possibility for an electrostatic generator. If you just have the jet turbine, an electrostatic generator, and a thruster, now suddenly it makes sense as a precursor, as a hybrid to purely electric propulsion. But that would require fusion. But it's still a step in the right direction. So the air-breathing ramjet, this is taken from the article for Bolonkin. I have his link at the end. I would strongly, if you're interested in this, please start with the Bolonkin article to give you an overview. So you have injectors at the entrance, electric field, they're injecting electrons, they're ionizing air. This is not just ions, though. You're also accelerating electrons, and you're pulling the air through it. You have a collector at the end. It's actually very simple in that respect. But electrical energy is converted into kinetic energy by collisions, as well as accelerating electrons. And starting out even at 1 million volts at 1 amp, that's actually, for my dissertation, that's what we're aiming for in the lab. I think that's a meaningful target that's necessary. There has been a lot of research at low power, low thrust, and with no air moving through the engine. In fact, one of the premier studies on this that's often quoted, they said the efficiency was less than 1%. Most of the energy was lost in the form of heat. Well, what they found with some subsequent studies, some of it with coronal discharge in wind tunnels, is when you get air moving through it, your efficiency jumps up incredibly. And actually, there's a French postdoctoral team that has applied. The pandemic might have changed this, but there's a French postdoctoral team that is wanting to test one of these thrusters in a wind tunnel because it hasn't been done. We've observed coronal discharge, and that's what this is, but not as a thruster, because they have found your current and your voltage can increase as you start moving. Essentially, your dielectric through it, because the air is your dielectric. And once it starts moving, things change. And if we can get more amps, what we see is more amps and more volts are possible before breakdown. We don't know how that changes over the course of the range. We don't know. And that's what's exciting about this. What's physically possible, and what we don't know. There's so much room in this field. Everything from the types of emitters you're going to use, the length of the cavity, thruster cavity, what type of emitter geometry are you going to use. We also have to deal with keeping the charge even, because it's going to build up an electric charge going through the air, and also just from the engine. Nothing's 100% efficient. You're not going to capture all of these electrons on the back grid. So you're going to start to become positively or negative charge. So you need ion injectors for that. So it's a whole new area of propulsion. So a lot of different aspects, but that's what makes it fascinating. So why the ELECTRET generators? We talked about them at first glance. I get two responses to this usually. One is indifference and ridicule, and they're kind of, maybe they're being polite when they're being indifferent. But the other is fear. Like, oh my goodness, you're talking about a megawatt for a test thruster, or at 10 million volts at 10 amps, and you want to put this in an ungrounded aircraft? Well, we have to do the research. Is it possible? We don't know. But that's the beauty of it. If you want certainty, there's death and taxes. And that's what I learned out in the desert in Mojave. And one of the things that the American aerospace community brings to it with the small entrepreneurial companies, they take risks. And I like what Burt Rutan says, that research is what we're doing, or it ought to be what we're doing when we don't know really what we're doing. And if you watch a video, it's called Under a Black Sky, about Spaceship One and that program, you really start to realize what kind of risks they were taking. And he talks about it. And he says, research should be when half of the academic and professional community says, won't happen, not going to happen, impossible, you're wasting your time. And the other half goes, well, maybe, but probably not. And you look at the Wright brothers. What qualifications did they have? They were bicycle mechanics. They had a very good idea of the mechanical systems, and they built wind tunnels and test platform to test their designs. And it took them a long time. And when they did finally build the Wright Flyer, it wasn't a very good airplane. So keep this in mind. There's no aha moment where everything works. Like, no, people are going to laugh, ridicule. You're always going to be low on money. And when you do finally build something, it probably won't work very well. So understand that. And that's why you want this to be something that you're truly passionate about. Because if you're not, then man, there's better things to go into. There's better ways to make a living. But the Walmersdorf machine is actually probably the best application for this, for a modern application. And there are two main areas to focus on with this that I'm going to be focused on, because you cannot consider just the thruster without the power supply, because at its root, like most problems on Earth, it's a power problem. If we had unlimited power, we don't need to be as efficient. Efficiency on this is another issue, but the generator must be tested and developed alongside the thruster, I'm convinced, because to get that power level that's meaningful for a meaningful thrust density, we have to have the right generator. And we don't really know how to size the generator until we have the thruster, because there are a lot of unknowns. So developing them together, even if it doesn't work, no one's built a hybrid jet turbine ELECTRET generator before. And there are several different applications for this. But that's essentially what we're looking at. This is a picture of Walmersdorf generator. And, the ELECTRET generator, now current research is on making it very, very small. Like triboelectric nano generators are being looked at for sensors, for different very small electronics. And so they're looking at dielectrics for that and ELECTRET substances, because there are two main things. And this is the only applicable, this is the only real choice, is trying to develop this. So what are the weak points? Well, and this article is at the end as well. Researcher named Matthews in 1962. It's a great article. Robert Matthew in 1962, he stated that the use of electrets in electrostatic generators for space, it's ideal. He put two and two together as well. It wasn't just the Russians. He says, ELECTRET generators that use electrets instead of magnets are the only real, I'm paraphrasing, you'll want to read the article, but he says if we want electric propulsion for space to actually get us to Mars in several months and to be able to get around the solar system, we need ELECTRET generators. And the problem was, he says, we don't have the materials because the surface electric charge density at that time, keep in mind this is 58 years ago, now 59, he said that we don't have the materials for it. And also there's a problem with bearings and seals that can operate in a vacuum. Electrostatic generators need a vacuum. It's like they're begging to be built and operated in space because you have to have the vacuum insulation. It's not a problem if you build it for space, but even the materials were a problem back in 1950 or 1962, so 59 years ago. So he said, develop the bearings, the seals, and the electrets, and this could become a reality. And we need it to become a reality because if we want to become a spacefaring species and have the propulsion to travel around without just burning things in an engine, this is what we need to do. And so I would highly encourage reading that. It's very succinct, and they built a small model. And so they said the key things we have to deal with, and right now, this equation, this is how you get amps, the Imax, out of an electrostatic generator. I also post this. There's a researcher in Brazil who, with the University of Rio de Janeiro, he's been focusing on electrostatic generators, mostly for demonstration purposes, but he's building real hardware. But again, this has been hardware that's looking for an application. And I believe high thrust ion drives are that application. So we can get the volts, that's not a problem. But how do we get the amps? Because electrostatic generators, yes, you can get 100,000 volts. You can get a megavolt. But we need 1 amp at 1 million volts. So let's focus on the amp problem. There are two real variables we have control over. 3 really, but when you look at the electrostatic generator, you have the surface area of the electret that's spinning around. And so that's our R max squared minus R min. So the disk is going to have a certain area. And we do have control over this. We can get more amps out of it, making it bigger. But electrostatic generators need to be very smooth, and they need to be very rigid. You don't want things flopping around. In fact, in the 1930s, they were working on the Wimshurst generator for particle accelerators, and they tried all kinds of different substances, and they thought like the centrifugal force would help smooth it out. They were going to use paper and some different things, and they said, no, do not use this. We need something very, very stiff and very, very smooth, because when it starts to wobble or deform under the electric forces, you turn your DC generator into an AC generator. And for an electrostatic thruster, that's not very good. I don't even want to really think about what could happen. You end up with a very interesting problem. So the disc needs to be a certain size, and that's going to depend on the material. It needs to be a very good dielectric. It also needs to have really, some ceramics are good for this. Barium titanate is good, but it also needs tensile strength because it's going to be spinning at a high RPM, which leads me to the next variable we can control. I call this our only free lunch. F is rotations per second. And we can make it faster. And the faster we make it spinning, especially with helicopter jet turbines, even like RC remote control model helicopter turbines for models, these can spin at 150,000 RPMs. So, we're talking 2,500 rotations per second. So very fast. Then, of course, we have the problem with the bearings when we go very fast. Well, we're talking about a vacuum insulated. It has to be vacuum insulated. Otherwise, it's going to break down and you're going to have lightning in your generator at 30 kilovolts per centimeter. And so we can't get the voltages we need. So it must be vacuum insulated, which also provides a benefit. It's like this thing was designed to be in space, because it really was. With a vacuum, we've not only insulated it electrically, and now we can get higher voltages, but we have no fluid friction. And so we can achieve a very high RPM to get our amps. I'm shooting for 1 amp. So that's the goal. So then using, okay, we have to worry about bearings, which is, of course, is a problem, especially in a vacuum. How do you lubricate bearings in a vacuum? It's a very old problem. Matthew talks about it as well. Well, with magnetic bearings or even electrostatic bearings, you have parts that are not in contact with each other. And these are being used more and more now. Magnetic bearings in a vacuum with this type of generator, and because it's electric induction, we're not using friction, we're using electric induction, you have no moving parts and virtually no friction. So now we've, at least as a thought exercise, solved the problem with rotations, and we can get very high rotations. It brings with it other problems, like if something breaks, if the ceramics shatter, and now you have shrapnel going very, very fast that's electrostatically charged, and again, you have lightning in your generator. Very bad. So RPMs, rotations per second for this equation. Now, for the Pmax, that's the surface charge density on the ELECTRET. And at atmospheric pressure and in atmospheric air, that ends up being 26.55 microcoulombs per meter squared. So very, very low charge density. There are new substances now that are being researched and used for very small electrostatic generators for electrets. Of course, Teflon, PTFE, we're getting up to 660 microcoulombs per meter squared. It's a lot better. It's like 24, 25 times the strength. Then some others, it's like Parylene HT. It's going up to 3.69 millicoulombs per meter squared. So that's 136 times the surface electric density as atmospheric. And so now we're talking. There's another one that I just read, and that's the thing about these. It's being researched, and very few people are putting it together, and no one's actually put the whole thing together because it's an entirely new field. And that's what's exciting about it. And collaborating with people all over the world, whether it's the French, the Brazilians, the Indians, the Americans, Canadians, the Ukrainians, I think it's an exciting time, because if this works, if we can develop this, we're going to solve a lot of our problems with space travel. So better substances for electrets, and also, bearings and RPMs. That's what we have to focus on. And so it's one thing to do it. That's another thing I learned in Mojave. It's one thing to put it down on paper. It's quite another to say, okay, go out and build it. And what I loved about that experience was that in the morning we had our ideas, we would write them out on the board, and then you go to the shop and build it. And so what I'm going to be working on for the next 3.5, 4 years for my doctoral studies, not just theory, but we need to build real hardware. And we focus so much on software modeling, and that's great. And we need theoretical models. But once we have a basic model, we need to go build real hardware, because otherwise we end up with rockets that take 20 years and cost billions of dollars but don't do anything. Or we have paper rockets or just great ideas that just never really go anywhere. Look at the Wright brothers. They didn't have millions of dollars. They didn't have PhDs, but they had a solid understanding of the fundamentals. They tested things. They built real hardware, and that's why we remember them. And the same thing with rockets. There are some very small companies that tried some ideas. One of them, like you look at X-Core, and they put a liquid rocket on a Burt Rutan Long EZ kit plane. And I remember hearing about when they were trying to recruit pilots and engineers for this. They're like, yeah, we're going to put a liquid rocket on a small plane. Like, well, how are you going to do it? Well, we have an idea, but we're not really sure. That's why we need you. And I was just really fascinated by that. Like I talked about, rotations per second is the only free lunch, and surface charge density. Different substances, parylene HT, barium titanate, Teflon. They're looking at some newer materials, and we can start putting these together. Experimental possibilities. I think this is a system that's begging for a test bed for a lot of reasons. It can't just be a one-off where we go, oh, we did it and it works, because there's so much. And in the literature, I got that impression too. There's a study done where they looked at different electrode materials like tungsten, steel. They looked at different geometries. Some were just sharpened into points. Some were made of wires. Some were like cylinders, even different lengths of the thruster. As you increase the length, you can increase your voltage and you can increase your thrust, but nobody's done it. And part of the reason they haven't done it is because they've only looked at very low power for a couple of reasons. But that's why we have to do this at the same time. So coming up with a form of some sort of test bed, we're going to need a micro turbine. Then we're going to have to design some sort of ELECTRET generator. It will have to be vacuum insulated. It will feed into a capacitor bank, charge them in parallel for however long. Like, it doesn't have to be in real time. If it takes 4, 5, 10 hours to charge, that's fine. We're going to learn about our bearings. We're going to learn about the vacuum seals. There's so much we're going to learn about this just from putting together the turbine and the generator, because it has applications in pollution, for like electrostatic precipitators, radiation shielding. There's a lot of applications. So we're going to do that, feed it into a capacitor bank, and then run the experimental thruster at however many seconds. We'll have to look at it, size it, what's available, what's the cost, but set up a test bed for this. We're also looking at multiple stages for the thruster, because they've done it with 2 stages. And again, it's complicated. Do you run the first stage at this voltage, the second stage at that voltage? Because they're finding out it can become counterintuitive. But multiple stages, what's the optimum voltage? What's the optimum length? Now, and then once we start moving air through this, how does that change the equation? Because we know it does. So very interesting, but it needs a test bed. Okay. So, and at 44 years old, why do I want to do this? And one of the benefits of being middle-aged is that we gain hopefully a little bit of wisdom in how the world works. And I realized that people can chase money and fortune and fame and all these things. But if it doesn't get you out of bed in the morning, it doesn't really matter. Money is not the key asset in life. Time and energy is. And I wanted to work on something that got me out of bed in the morning. And even if it doesn't work, think about what we're going to learn. And that was my approach. Getting out of bed and working on something I love to do, love to study. That's living to me. Not getting up, going to a job I hate to pay for things I can't afford. That's not life to me. So, and the possibility for this really is the closest thing to working on the engines of the Millennium Falcon that we can get in our time. It's not warp drive. It's not antimatter drive. It's possible. It's extreme, but it's possible. So Anyway, I know I've gone over a lot, but these are sources for additional information. I'd be happy. This is a good place to start. I would start with actually the last one, the article from Bolonkin, then go to the Matthews article, and then this website from Brazil. Amazing. And what I like is he's building real hardware, and he's done it for longer than I've been alive. So that's a really good source too. I can send this. This will be available somehow. So, all right. Let me. Okay. So, could you hear, see everything okay? I didn't really get a
Yes,
response.
sir. It's a very fine, sir.
Okay.
Uh,
So that's.
so
Go ahead.
wait for me. Any students have any doubts? Any students have a doubt?
Uh, could you repeat, please?
No, sir. So nobody can any doubts, sir. You continue, sir.
Oh, any thoughts? I mean, if you have questions, please feel free to ask and check out those articles. This pandemic in Ukraine, it's kind of been like normal life, but not really. There's a say that 2020 is the year that nothing happened, but everything changed. And so I just learned, to make the most of it. And, oh, sir, please hide the taskbar. I can't read. Oh, was there a problem? That was at 8:45.
Sir, no problem. You continue.
Okay, well, Mari was saying, could you please hide the taskbar because I can't read? But maybe that was when I finished. Yeah, so we've been, at home, and I just decided if I'm at home, I ordered a whiteboard and just started letting my ideas flow. And I'm not a genius. I'm not Elon Musk. I'm just someone who loves space flight. And I've been at home for almost a year. Oh, and it's snowing outside. But that's Kiev. But, I found that this time we're at home. We have the internet. There's no reason to be bored whatsoever. We have the collective research and wisdom and knowledge of the world available to us. And so, I'm going to be working on this for the next 3.5 years at least. I started a small company to focus mostly on this, but also I like the idea of the inflatable space tower, even to several kilometers. And then radiation shielding with electrostatic generators, electric fields for active shielding in space. This is a real problem. And NASA's done some studies for radiation shielding with electrostatic forces. And we need generators for that. And electrostatic generators have a lot of positives. They're not considered very efficient, but when we look at the new materials, we look at vacuum insulation, we look at magnetic bearings, and even if you look at their weight to their power to weight ratio, they're superior to magnetic generators. They're looking at about 5 kilowatts per kilogram. So a megawatt electrostatic generator for a thruster, that's 200 kilograms. That's not some crazy number. That's actually doable. And if we tried to do the same thing with magnetic generators and then either rectifiers and DC to DC converters for the voltage and the engine to turn it, it makes no sense. But this is something that has so many different possibilities, and but we need the power. So, any questions? Any thoughts? Don't be shy.
So no doubts in anyone, sir.
No. Well, so tell me about your school. You're at Infant Jesus College of Engineering.
Yes, sir. I'm studying in Infant Jesus College. Yes, sir.
Eh, Okay.
Oh, uh,
So what kind of things do you like studying? What interests you?
so I'm interested in propulsion, sir, in rocket propulsion.
Rocket propulsion? Okay. Yeah. And
I won't
yeah.
join the college in aeronautical engineering. My projects are focused on uh, cryogenic engines.
Did you say cryogenics?
Yeah, yes, sir. Cryogenic.
Yeah. Yeah, that's what I like about all of this. It's a new field. I mean, even just space in general. I'm 44 years old, grew up at the end of the Cold War, and all you had back then, you had the Soviets and you had the Americans, and that's who you had to choose from. And what's sad is that in all of this time, we didn't go back to the moon. We've had robotic exploration that's amazing, but what a lot of people were disappointed with, Jeff Bezos, Elon Musk, and a lot of others, they were disappointed that there wasn't more of a push. And, we've wondered, like, why is that? Now, I'm no Musk or Bezos or anything like that, but I can be inspired by them, and so can you. Um, what I see we have a lack of is taking risks. Look at the Starship and even the Falcon 9s. When they were talking about landing rockets on a ship, a drone ship out at sea, uh, the major players laughed. Even none less than Neil Armstrong and Buzz Aldrin were in Congress telling the U.S. government that Elon Musk doesn't know what he's doing. These private companies will never be successful. Don't fund them. They don't know what they don't know. They're just, they're just messing around. The first and second men on the moon are dissing and telling you it can't be done. Think about that. You know, um, wow, that's a rough day. You know, so but taking that risk, and that's where studying problems from their fundamentals. What is the fundamental problem? How can we possibly solve it? And like Einstein said, imagination is more important than knowledge. And I really believe this. I find myself thinking this more and more because knowledge really is finite. We only have so much knowledge, but imagination, and I'm not just saying ludicrous things, but to imagine what could be and then go after it because it's very difficult and it probably won't work. But if that excites you, then go after it. And, electrostatic generators are something that they're deceptively simple, but there's so many aspects to this. So anyhow, I've been talking for almost an hour. I hope this was interesting to you. Um, and
Yes,
help.
sir. Yes, sir. It's very interesting seminar, sir. But it's a time to
Okay.
switch to another session. Yes, sir.
Okay.
Thank you, Mr. Varun. That is very
Thank
yeah,
you very much.
it-
Appreciate it. And
wonderful session, sir.
if anyone wants to email, ask questions,
Yes,
read those, definitely check out those links. So take care, and hope to see you again.
thank you, sir.
Thank you. Bye bye.